такую. Куда же нажать-то?
Может быть, у вас из-за того, что вы мне отдали хоста?
Может быть.
Давайте я вам обратно отдам.
Сделайте ко-хост, может быть, достаточно.
Так, а вы ко-хост, нет? У вас...
Да, я ко-хост, да. На какой? Но это он другой, да.
То есть у вас не тот аккаунт, да?
У меня нет, аккаунт тот.
А вот теперь?
Прибора.
А теперь?
Сейчас я другой прибор.
А теперь вы можете? Я вот вроде сделал вам ко-хост.
Да, тут что-то изменилось, да. Вот, запустил запись. Запустил. Ага, спасибо. Так. Так. Всем здравствуйте. Видно чистый листочек с заголовком?
Да, видно.
Отлично. Так, мы продолжаем вот эту тему указанную. Так. Значит, мы почти узнали, что такое когомология Чеха. Вот, ну, я не знаю, давайте я вам покажу конец предыдущей лекции. Вот, значит, напоминаю, что для того, чтобы вот определить комплекс Чеха, мы просто берем открытое покрытие и в качестве Q-форм, Q от цепей, извините, вот берем такое пространство, пространство сечений на всех Q-крат. Oh, sorry, I should have. Is Keke present? I hope.
Not yet.
Not yet.
Так что можно по-русски, наверное.
Ну тогда, Коль, следите, пожалуйста, если
да,
она появится.
Я буду смотреть, да.
Знаете, сейчас у меня, кажется, есть прямо драфт письма, ей я сейчас быстро тогда отправлю, что если она появится, чтобы она как-то...
Да я вам скажу, не, ну ладно, может, нет.
Видно будет.
Не будем сейчас, да.
Ладно, хорошо. Хорошо, не будем тратить время. Так. Хорошо. Значит, вот это пространство чеховских коцепей, вот написано, нужно брать сечение нашего голоморфного расслоения на Q-кратных пересечениях. Ну и сумма по всем таким пересечениям. Вот. Дифференциал Чеха я тут написал для первых двух случаев. Теперь что еще мы узнали? И тут мы остановились, да. Так что вот давайте продолжим, но только я все-таки в отдельном файле это буду делать. Значит, это был, наверное, пункт 1.2. Ну, тогда написать я тогда все-таки по-английски буду. Нет, это трудно, конечно, говорить по-русски, писать по-английски, довольно глупо.
Тогда говорите по-английски.
Наверное, придется по-английски. So, we continue the subsection Czech homology. So let us see what are the first homology groups of the Czech complex. So in general, we denote the Czech homology HQ. Which, again, I repeat that in principle, these objects depend on the covering. But then I say a couple of words. What should we do with this? But up to now, everything depends on the covering. So the Czech cohomology, but I do not explicitly indicate this in my notation. So here I write only the manifold, the complex manifold, and E, a holomorphic vector bundle. Then the Czech cohomology of X with coefficients in E is the kernel of the differential quotient by the image of the differential is always. Was it delta, right? Delta Q image delta Q minus 1. In particular, H naught it is a subspace in zero chains, which is annihilated by the differential delta naught. So it's the kernel of delta naught, and this is the following thing. It's set phi alpha, where phi alpha, each phi alpha belongs to the sections of the holomorphic bundle over the element of the covering Q alpha, such that for any alpha and beta, such that the intersection is non-empty, we have that phi alpha restricted to the double intersection and phi beta restricted to the same thing are equal. So in principle, it's tempting to say that the space of the zero cohomology of Czech cohomology is the same as this global sections of the bundle. This would be true if we take the limit over the coverings, the direct limit over the decreasing coverings. So in principle, there is a notion of cohomology of a holomorphic bundle which does not depend on the covering and does not use d-bar operator as we started with last lecture. But I don't want to give this general abstract definition. So let me somewhat informally say the following thing. Informal remark. There is a general definition of cohomology for E being a holomorphic vector bundle, or more generally sheaf of modules of holomorphic functions, but we don't use this notion. So I write just holomorphic bundles here. Such that this cohomology turns to be equal to the limit by the limit of coverings, I mean the limit of decreasing coverings, smaller and smaller. However, if we choose a sufficiently small covering, then the Czech cohomology equals the limit of coverings. Sufficiently small means that, in particular, the criterion of sufficient smallness is the following. Well, for example, that for any alpha, beta, and so on, the cohomology and any q greater than 0 the cohomology, these are unknown for us, cohomology of a holomorphic bundle considered over the multiple intersection vanishes. This means that the open sets considered as elements of the covering, as intersections, triple intersections, and so on, are sufficiently small, so small that the bundle doesn't have cohomology over such sets. Then this equality holds. So the model is that, for example, if you choose Stein open sets and such that the intersections are Stein, then everything is okay, and you don't have to take the limit, this limit over the coverings.
What do you mean by Stein?
Stein is a property of an open set, not of a manifold, which I don't mention. It's not the subject of our study, which guarantees this property that cohomology vanish. In particular, Stein means that there are sufficiently many holomorphic functions. It's Stein is very similar. Stein in complex analytic geometry is, to a certain extent, an analog of affine varieties in algebraic geometry. In particular, affine varieties are Stein manifolds also. In the case of curves, for example, a disk in the complex plane is a Stein manifold, or a curve without a point is also a Stein manifold. So in the case of curves, let me write this. For example, actually, to be strict, I guess I need, wait.
Can we think that it's enough just to be contractible, or maps have to be contractible and it's enough?
No, I'm not sure. It's not a purely topological property. It's a holomorphic property. It is certainly not necessary to be contractible, but whether it is sufficient, I forgot. I'm afraid to say. In the case of curves, one can always consider a covering consisting of two sets. Consisting of, when X is represented as U union with X minus point, and where U is a neighborhood of that point, some small neighborhood, like a disk. Just to give you a feeling of what, in particular for complex, what we call Riemann sphere or CP1, we can use the covering consisting of two copies of a complex plane, as usual, with coordinates z and z minus 1. Okay. Now I'm going to prove you the following statement. It's sort of Dalbo theorem. Dalbo theorem is an analog of the RAM theorem in topology, but you shall see. Okay. So for X and E as above, we have the following isomorphism, that d-bar cohomology of X with coefficient in E, as defined in the previous lecture, is the same as Schiff cohomology or Czech cohomology of X with coefficients in E. Let us first see the idea behind this statement, and then we shall, a little bit later, we shall prove it formally. But in principle, what I'm going to say it can be made a proof as well. Idea of a proof. Let us start with again. Let us demonstrate this for a small q, for q equals 0 and 1. What is H0 d bar xe? It's the kernel of. But it is, I think I denoted it as nabla bar. I mean that a holomorphic vector bundle we can represent as a smooth bundle with nabla bar d-bar connection, as we discussed. and nabla bar is a flat D-bar connection. So I continue. The zeros cohomology group is the kernel of the operator nabla bar, which acts from smooth sections to smooth 0-1 forms. So it acts from what I denoted lambda naught xe to lambda 1 xe. And what is this kernel? It's just the space of holomorphic sections, right? By definition, by one of the definitions. And we have seen just a minute ago that the Czech cohomology also is the same as the space of sections. I will just scroll up that you see, but let me just finish writing. So let me come back for a second. Where it was? Over here. Here what have we checked? We saw that the zeros Czech cohomology is a set of local sections which agree on the double intersections this way. Therefore, if the covering is small, it is exactly the same thing as a global section. Does anybody understand why in this particular case for zeros cohomology, I'm saying that the covering still should be small enough? The point is that on one hand, if we are given such a set of local sections which agree on double intersections, of course, it always defines a global section. But vice versa, it may not. It can. Yeah, in the opposite direction, it may not be true because. Wait, am I right? Just a second. Okay, I don't want to waste your time, but if I think I will, if somebody is interested, I can say. But anyway, we should always work with small coverings or good coverings, if you want. Okay. Now, so this was like first example, and second example is the following. Let us consider an element in D-bar cohomology of degree 1. So we take some representative of a class, of a cohomology class. So omega is a 0-1 form. I better, let me correct here. I better write here 0-1 for clarity, okay? I don't remember what was on the last lecture, but still. so it's a 0-1 form on X with coefficients in the vector bundle, which is d-bar closed. Now, if the covering, now you see again the necessity of having a small covering. If the covering is good, then omega restricted to each element of a covering is exact by Dalbo lemma. D of some phi alpha, where phi alpha is a smooth section of the smooth bundle.
Sorry, by D you mean nabla or not?
Yes, thank you. Nabla bar.
And above also.
Yes. Thank you very much. Now, if we consider these phi alphas on double intersections, what we have is that nabla bar of phi alpha minus phi beta equals 0 on U alpha beta. Hence, the set phi alpha beta defines a, I better write it, wait. Then phi alpha beta is a holomorphic section on the double intersection of the holomorphic bundle. And hence the set of such phi alpha beta defines Czech chain of degree 1 and one can check from the definition of, oh wait, I did not write this. Let me write in this way. By phi alpha beta, I understand the difference. Phi alpha minus phi beta. Phi alpha is not holomorphic, but the difference of two of them is holomorphic. But nevertheless, the fact that we represented this phi alpha beta as a difference of two guarantees that on triple intersections, the one cycle condition is satisfied. Therefore, the cohomology class, therefore we have a closed chain. Its cohomology class defines a Czech cohomology class H in H1, which by assumption is the same as unknown for us, but I mean, the cohomology and coefficients in a bundle. Okay, but we shall see the proof later for arbitrary degree of chains. Okay. Now, in order to accomplish the proof which I mentioned, which I have in mind, let us make a digression in algebra. So let us call this.
Maybe there are some questions to this.
Yes, please ask questions. You will always interrupt me, actually. Any questions? Okay. Now will be the subsection 1.3.
Sorry, I have a question. If nobody
sure.
When probably I had to ask it before, but when you say when we define Czech cohomology, and
Yes.
we say that differential sends local sections on some neighbors to some section on intersection. Yes.
Yeah.
We need to have local trivialization of vector bundle.
No, the notion of section does not require trivialization.
Yeah, but you have to compare somehow sections defined on one neighbor with sections.
There is always the map called restriction map. So if we have, say, X and Y complex manifolds, whether Y is open in X or closed doesn't matter. In both cases, we have the map.
Yeah, I understand. So, yeah, I understand. So the local sections are just like holomorphic functions on base with values in total space. Or
yes, and you can restrict them to a subset.
Okay. So the computation is like a computation in a ring of holomorphic like ring of holomorphic functions. Yes, this is not.
Yes, but I would not say the word ring here because it's rather about modules over the ring. But
okay.
Otherwise, yes.
Okay, I see. Thank you.
Okay. So first, the notion of a complex of vector spaces, which I guess everybody knows, but still. To be more specific, it should be called cochain complex because the cochain and chain complexes differ only by the labeling, whether the differential decreases or increases the grading. So it's a set of vector spaces and maps between them denoted in this way, such that the product, the composition of the neighboring errors gives 0. Or as a whole, we write d squared equals 0. Then one can define the quotient spaces called homology groups. So this is just to denote that they depend on the complex. Due to this property, the kernel contains the image. Therefore, it can take the quotient. In most convenient cases, we deal with bounded complexes. Which means that CQ is not zero for a finite number of Qs. And the spaces itself, in practice, we deal with situations where the vector spaces CQ are finite or infinite dimensional. Both cases are important. Okay. Now, let us consider exact sequences of complexes. Let me write. We consider three complexes. And maps between them, better to say morphisms. And say that they form a short exact sequence. It's a term. If we write it this way. So A dot is a complex, B dot is a complex, C dot is a complex. And let's, as you know, the morphism between them as say phi and phi. In principle, it's logical to put dots also near morphisms, but this is a little bit too much already. If we have, if we write it in this way, then kernel of phi equals image of phi. Exactness, this is exactness in the middle term. Also, the image of he should be the whole C dot. So he is surjective. So in this sense, the image of he equals the kernel of this map following it. And phi should be injective. This is exactness in the first term. Now, let me remind you that, say, phi mapping A dot to P dot is a morphism of complexes if it is a morphism of vector spaces, that is linear map, which commutes with the differential or respects the differential. If it is a linear map such that dB, which is differential in the complex B, composition with phi is the same as phi composition with dA. Where do we meet?
Sorry, you have phi above and phi above and phi here. It might be confusing. You have phi as
on another page.
no. On the right here you have phi.
It's the same phi. It's the same phi.
But
you mean this phi and this phi?
Yes.
It's can be the same phi.
So A, B, and C are all complex short exact.
No. Each letter denotes a complex.
A, B, and C are all complexes. Yes.
Yeah, three. We took three complexes A, B, C.
Okay.
And morphisms between them. And now I describe what the term morphism means.
Okay. Thank you.
An example of a morphism of complexes in geometry is the operation of a pullback. If we take a holomorphic map of complex manifolds, then on differential forms, we have a pullback. And since the map is holomorphic, it preserves the PQ type, the Hodge type of forms. And we have the pullback, which maps, say, PQ forms on Y to PQ forms on X. And this is a morphism of Dalbo complexes. And that is, it commutes with D-bar operator, right? Also with the RAM. For the RAM, it's also a morphism of complexes. And second thing we should recall, any morphism of complexes induces a map in cohomology. Because of this property. Мы до 4, да?
Да.
Вообще очень мало. Конечно. Now, one of the features, or what properties, why the short exact sequences are important is that given a short exact sequence, we have an exact sequence in cohomology of those three complexes. Of complexes, A, B, C, we get a long means just long. It's not such a technical term as short. But the most important thing is that we get a long exact sequence. Namely, the following. So I don't know where it starts and where it terminates. If the complex is bounded, of course, the cohomology are also bounded. But since I didn't specify whether, for example, in very often we deal with complexes which start from the 0 degree. But it's, strictly speaking, it's not necessary. We should consider complexes starting from any degree. Therefore, here in the general proposition, I cannot start from H0. I start from somewhere, from these dots. And the non-trivial thing is that here we have a map to HQ plus 1 of A. This is not obvious. It should. These maps. This map is induced by the morphism phi. This map is induced by. Do you understand? Don't you have questions about when I said induced? About this recollection? No question about this. Very good. Induced by phi. And this is the whole so-called compoundary morphism, which I will describe shortly. And the latter thing is defined as follows. So we should take a class in the complex C, say gamma, be a representative in the cohomology of C. So d C gamma equals 0, right? Now, since we had an exact sequence, the morphism he was surjective, right? So since he is surjective, he acting on K-chains, not on cohomology, but on K-chains it was surjective. We can write gamma as he of some beta, where beta is in the complex B of degree Q. Now, beta does not have to be closed. However, the differential of beta is annihilated by he, right? Because it would be he of d beta would be d of gamma, or d of he of beta, because he is a morphism. And this is d gamma, and this is 0, right? Now we see that beta is d beta belongs to the kernel of he, which is the same as image of phi, okay? Because the sequence here was exact by definition of the exactness. Therefore, d beta equals phi of some alpha, where alpha belongs to the complex A of degree Q plus 1, right? Now we notice that phi of d alpha equals 0, because it's the same as, because d and phi commute, right? And since phi is injective, we have that d alpha equals 0. Therefore, alpha is a closed K-chain, and it defines an element from HQ plus 1 of A. Thus, we have we obtain a map which to a class of gamma gives a class of alpha. That is the map from, it's often denoted by delta, don't confuse with Czech differential. Delta, which maps HQ of C to HQ plus 1 of A, co-boundary map, co-boundary morphism. And one can check that the above written sequence in cohomology is exact. Just starting from the definitions. Actually, this is a very powerful tool for computing homology. And it often happens and when you know cohomology of two complexes, then you can learn from this exact sequence cohomology of the third one, provided some useful properties hold. I mean, in examples, it works, not as a general rule. Oop. Okay. I guess this is a good point for a break, right? We agreed to make a 10 minutes break and then finish at 4:10. Okay, see you in 10 minutes, and you can ask questions now. All right, I'll be available for questions during the break. Okay, let us continue. No. Now, let us consider the following trick in this abstract setting of complexes of vector spaces. Which will be an application of the proposition concerning the short exact sequences. So let me put here black box. It will be a proposition, the proof of which I will give as an exercise with a hint. Now, let us consider the situation when we have many complexes related by morphisms which themselves form a long exact sequence. Long means nothing, just several. So what I mean, we have complexes labeled by some letter, say, so each complex will be C dot labeled, say, by alpha. C dot labeled alpha plus, C dot alpha plus 2, and we have maps, morphisms of complexes. And we suppose that the whole thing is bounded sequence. By bounded, I mean, as always, that there are only finitely many non-zero terms. So each error is a morphism of complexes. Now let us assume for convenience each complex starts from degree 0. Which means that CQ alpha is 0 for Q less than 0. And also probably, again, for convenience, let us probably this, no, about what concerns the index alpha, we don't probably need any assumptions even for convenience, just boundedness. All right. But the crucial thing is the following. If we have that the complexes are almost acyclic, which means that all cohomology except the zero degree vanish if we have that HQ of C dot alpha is 0 for Q greater than 0. For less than 0, they vanish because the spaces of chains vanish. But let us assume that cohomology of positive degree vanish. Then wait. Sorry, let me. I'm sorry. No, not this way. I beg your pardon. I need another notation. Okay, let me write as follows. I have to erase, sorry. Let us write the following sequence. We start from a complex A. So I explicitly write the first non-zero term in this sequence. So 0, A dot. Then it will be C dot 0, C dot 1, etc. C alpha plus 1, and so on. And it terminates somewhere. And about the complexes C, we assume what we assumed. And nothing is assumed about A. Then the proposition says that the cohomology of A can be obtained as the quotient H naught. Let me denote sorry, I'm just looking for an appropriate letter. Let me denote by this letter would be good. Okay, let me denote this morphism of complexes by D naught, D1, D alpha plus 1. So then the proposition says that the cohomology of A can be obtained as cohomology of as the kernel of dq note that these all dq's are morphisms of complexes, right? Then they induce maps in cohomology. As always. And here I use, and for those maps in cohomology, I use the same letter D. So I can consider map from cohomology H naught of CQ to H naught of CQ plus 1. And consider the kernel of this map. Now I can do the same with the image of DQ minus 1, which maps from H naught of Q minus 1 to H naught of Q. And note that since we assumed that the sequence star is exact, that it's DQ composition with DQ minus 1 is 0. Therefore, this quotient makes sense. In other words, the image of DQ minus 1 belongs to the kernel of DQ. How should we prove this? This is one of the central things actually in applications, and we are going to apply it to our situation with D-bar cohomology. And this should be an exercise to finish the proof. Yeah.
Можно спросить?
Yes.
Сейчас, если последовательность точная, это ведь значит не только, что d квадрат равно нулю, но еще и что это, что, собственно,
I will mention now. Yes.
собственно, кохомология равна нулю.
Yes, right.
И это означает, что h-q это с точкой 0, или я что-то пропустил?
Сейчас будет. In the sequence, or for the sequence, I better say, for sequence of complexes, C dot Q, C dot, say minus 1 Q. CQ plus 1. Exactness means assumption of exactness. Yes. Exactness means what you said, that image of DQ minus 1 equals kernel of DQ. For the induced sequence, in cohomology, HQ minus 1. Oh, sorry. It's not Q minus. H0. In each degree of cohomology, we get a sequence of morphisms. So this is the same letter, but another map. we don't have in general exactness. But we still have the composition of the neighboring guys just because such a property is kept when we pass from cochains to cohomology. Thus, we still have that the kernel of dq contains the image of dq minus 1 in cohomology. But they are not equal anymore. Therefore, the above written quotient does not have to be 0. Because here we use the action of D on cohomology. So this is just to fill the situation. And in order to prove, the hint is one should break the long exact sequence into short ones. In which, what do I mean? Say, first we start from the leftmost edge, where we have, according to our notation, and so on. Now we can obtain the following sequence of vector spaces, of complexes of vector spaces. And let me denote it, say, Z1 dot 0, where Z1 dot equals the kernel of D1 acting from C1 to C2. It simultaneously equals the image of D naught from C naught to C1. Therefore, due to the last remark, last equality, this one, we have that the map here is surjective. Therefore, the sequence is exact. It is a short exact sequence. Now, for the sequence consisting of this, we can write long exact sequence in cohomology. Then on the second step, and we should take into account the conditions, of course. And the conditions are that otherwise nothing would happen. The condition is that all the complexes are one-acyclic. I mean that the cohomology vanish for Q greater than 0. Then consider the following sequence. 0, Z1, C1, Z2, and so on. Then, collecting all the information coming from short exact sequences, one can come to the conclusion. Okay, we have 10 minutes, right? Now let us consider an example, an application of the above, and it will be the next subsection, I guess. 1.4. It will be called Dalbo theorem with coefficients. I mean, with coefficients in a holomorphic bundle. First, Dalbo lemma. It's like Poincare lemma for D-bar operator. Any D-bar closed PQ form is locally exact. D-bar exact. So in other words, there are no Dalbo cohomology on small, in a neighborhood, in some small neighborhood. For each point, there exists a neighborhood such that this holds. Now, Dalbo lemma with coefficients, local lemma, I mean, will be as follows. So X and E manifold, complex manifold, of course, and bundle. For any point, there exists an open neighborhood such that D-bar cohomology sorry, I should have formulated it with D-bar connection, of course. Again, X complex manifold, E nabla bar smooth vector bundle with a D-bar connection, which is flat. Then D-bar cohomology of X E. Oh, again, wrong. And then D-bar cohomology of this small open neighborhood with coefficients in E vanish for Q greater than 0. This is a consequence of the Dalbo lemma because in a neighborhood of a point, any bundle is trivial. In a small neighborhood of a point, I'm confused. In a small neighborhood of P, one can choose such a trivialization of our smooth bundle E such that the operator nabla bar becomes simply D bar, and then applies the Dalbo lemma. Okay. Good. Now, let us consider the following sequence of vector bundles with D bar connection. Just let us first to be probably would be easier to prove the following thing. Let me see. Okay, no, doesn't matter. Now I formulate what can be called Dalbo theorem with coefficients. Consider the following sequence of vector bundles, one of which will be a holomorphic bundle, and the other will be what you see. Consider sequence bundles. Oh no, I better write it like first I formulate this the sorry. No, it's faster to erase. The proposition is the following: that cohomology of a holomorphic vector bundle equals, I probably wrote it because we discussed the Q equals 0 and 1 cases. Where I write it in such a way. We can represent any holomorphic bundle as a smooth bundle with flat D-bar connection. Then we have two ways to define cohomology. One, say, in Czech terms, and the other in Dalbo terms. And both cohomology isomorphic. Since the time elapsed, I don't continue here, but let me just say one thing again, which I probably did not pronounce quite clear, about Czech cohomology and dependence on the covering. Czech cohomology as HQXE does in general depend on the covering. However, these cohomology groups computed for good coverings, which I also called small enough, however, are the same. However, these cohomology groups for good coverings are all the same. And they are denoted as simply HQ of XE. Okay? And they, in principle, they're the same as the limit for small coverings. Okay, thank you very much. Questions, please. Bad sign, no questions. Okay, then I stop the recording.